The possibility of extraterrestrial life has long fascinated humanity, and this fascination intensifies as scientists increasingly focus on Proxima Centauri b, the closest known exoplanet to Earth. This nearby world, orbiting the red dwarf star Proxima Centauri, is more than just another celestial body. It represents a tangible hope in our search for life beyond Earth. Recent discoveries by advanced instruments such as the James Webb Space Telescope have fueled these hopes. In a remarkable observation, the telescope revealed the presence of unusual bright lights emanating from the surface of Proxima Centauri b. This unexpected phenomenon has prompted widespread curiosity and speculation within the scientific community and beyond. What could be the cause of these unusual lights on Proxima Centauri b? Are they mere natural occurrences, or could they possibly indicate the existence of intelligent life beyond our own planet? For years, mankind has longed for, dreamed of, and actively searched for signs of life beyond our solar system. The desire to understand whether we are alone in the universe has driven scientists to probe deeper into the cosmos, using increasingly sophisticated instruments to look for any hints of life elsewhere. Any indication, no matter how small, suggesting the possibility of this long-standing fantasy has always been met with great enthusiasm. From radio signals to molecular traces, the scientific community has kept a vigilant watch. But recently, this watch turned into stunned amazement when the James Webb Space Telescope captured compelling evidence that many believe points to the existence of life forms in space. While exploring the vast reaches of the cosmos and transmitting critical data back to Earth, the telescope observed what appeared to be unique urban lights coming from the exoplanet Proxima Centauri b. These lights, described by some as urban in nature, have never been seen before in the context of space exploration. As their name suggests, these lights bear a striking resemblance to those generated by cityscapes on Earth, hints of illumination that outline infrastructure, activity, and possibly even civilization. The appearance of these lights implies the possibility of a distant city glowing in the night. The very idea that such illumination could be artificial rather than natural has captured the imagination of scientists and the public alike. The concept of an alien civilization existing within this neighboring star system has perplexed scientists, sparking a mix of wonder and skepticism. Each researcher who examines the data is equally baffled and intrigued by the implications. The notion that this could be the discovery they have all been waiting for, the breakthrough that finally proves we are not alone, fills them with both excitement and trepidation. If confirmed, this would not be a mere curiosity. It would represent a monumental revelation, the existence of intelligent life forms that have developed complex societies far beyond our comprehension, situated not in science fiction, but in the tangible reality of outer space. And we, as a species, may just be at the beginning of this astonishing discovery. Observing these urban-like lights from an immense distance of over 7 billion kilometers, NASA engineers have begun to wonder, how long have they been glowing in space? Have they been quietly shining there, waiting for humanity to develop the technology sophisticated enough to detect them? The James Webb Space Telescope, with its incredible power and precision, has made this level of detection possible. David Kipping, a renowned astronomer at Columbia University, has characterized Proxima b, the location where the lights have been sighted, as a celestial body with peculiar heating patterns that differ significantly from those observed on other known planets. Unlike conventional rocky planets that typically absorb sunlight and re-emit it in the form of infrared radiation, this particular exoplanet, Proxima b, demonstrates a markedly different infrared signature when compared with its host star, Proxima Centauri. This peculiarity in thermal behavior has allowed scientists to study it with an exceptional level of precision, particularly through the lens of the James Webb Space Telescope. The JWST, as it is widely known, is specially designed to be highly sensitive to infrared wavelengths. This capability makes it an ideal instrument for detecting subtle variations in temperature and light across distant celestial bodies. The thermal signature of Proxima b will likely play a pivotal role in helping researchers investigate the universal secrets that lie within its atmosphere. Taking full advantage of the JWST's state-of-the-art infrared imaging capabilities, scientists have developed a plan to use this telescope to unravel the atmospheric mysteries of Proxima b. They aim not only to study its unique heating patterns but also to assess its potential habitability. The JWST, with its exceptional infrared sensitivity, is uniquely equipped to probe the dark side, the night side, of Proxima Centauri b. Because it can pick up even the faintest light signals in the vast cosmic darkness, it becomes the ideal tool for verifying the existence of what may indeed be artificial city lights in the planetary nightscape. JWST's ability to detect what might be artificial illumination in the cosmos stems from its remarkable capacity to operate within an extremely narrow frequency band, one that is 1,000 times narrower than the band of light typically emitted by stars. This incredible sensitivity gives it the ability to distinguish even the faintest anomalies that might otherwise be lost in the overwhelming brightness of stellar radiation. Proxima b also exhibits an interesting relationship between its stellar features and its surface interactions. Its daytime hemisphere is reportedly adorned with solar panels, presumably collecting energy from its host star, while the planet's night side plunges into frigid temperatures. This stark temperature variation on Proxima b, largely dictated by its atmospheric composition, presents an intriguing topic for astronomers. The JWST is capable of effectively probing the planet's thermal emissions, providing vital data about its atmospheric properties. These observations could potentially reveal whether Proxima b has a thick, insulating atmosphere or a thin, unstable one, each scenario holding different implications for the potential presence of life. In addition to its sensitivity, the JWST's orbit around Earth aligns conveniently with the orbital path of Proxima b. This alignment allows for continuous and consistent observation of the exoplanet's diurnal, day, and nocturnal, night, cycles, which recur every 11.2 Earth days. This regularity makes it easier to monitor and record changes over time, lending credibility and robustness to the data collected. The next crucial step in the process is to assess the atmospheric chemistry of Proxima b in greater detail, with a particular focus on the presence of certain key gases such as oxygen, water vapor, and methane, elements widely considered to be critical indicators of habitability. If any of these elements, oxygen, water vapor, or methane, are detected in the planet's atmosphere, it could serve as compelling evidence that Proxima b is capable of supporting conditions conducive to life. The presence of such gases would not confirm life directly, but it would significantly elevate the possibility that biological processes are occurring, or have occurred, on the planet. However, this analytical process is extremely challenging. It involves the meticulous capture and analysis of the light rays that pass through the planet's atmosphere as it transits across its star. These light rays can carry within them valuable clues about the gases and molecules present in the atmosphere. Although the James Webb Space Telescope has powerful capabilities for characterizing planetary atmospheres, its focus is primarily on analyzing variations in the concentration of certain gases such as water vapor, carbon dioxide, and methane. Detecting oxygen, which is often regarded as a more definitive indicator of life, is more limited in the case of the JWST. Despite these limitations, the telescope continues to seek other elements such as ozone, a byproduct of oxygen, which may also provide essential clues to the planet's habitability. The presence of ozone could imply biological processes even if oxygen itself remains difficult to detect directly. It is important to keep in mind, however, that the JWST cannot explore all potentially habitable worlds. Its capabilities, while groundbreaking, are inherently limited, and it can only observe some of the exoplanets that are closest to Earth. Because of these limitations, astronomers are increasingly turning to ground-based observatories to fill the gaps. One such promising development is the Extremely Large Telescope, ELT, which is expected to become operational in 2028. This powerful new instrument will allow for much deeper investigation into the atmospheric structure and chemical composition of distant exoplanets, expanding our toolkit in the search for life. Scientists around the world eagerly anticipate the development of future space telescopes that will further enhance our understanding of planetary systems outside our solar system. These next-generation instruments are expected to push the boundaries of exoplanetary exploration even further. Although the JWST has its limitations, it remains an indispensable tool in the ongoing quest to unravel the mysteries of distant worlds. Its ability to detect minute differences in infrared wavelengths has already opened up new possibilities for understanding the environments of faraway planets. Future space telescopes will aim to overcome some of the JWST's constraints, such as the challenge of stellar glare, which often obscures